Hello, today we'll talk about illumination and shading. These are the today class objectives. We'll continue on our discussion on how to consider light during rendering models. Today, we actually specifically talk about this phone illumination to talk about how we can represent this non-ideal specular. Then we'll move on to the shading. Also, we'll talk about some of the difference between local and global illumination techniques. So also the last time we talked about the ambient diffuse term. Also we talked about the ideal specular term. So based on these discussion on last time, we'll continue on those techniques. Before we talked about the today's material, I'd like to summarize what we have talked about so far from the beginning of this course. So you might recall that at early on we actually talked about some of example of Julia set. Based on this Julia set, we talked about the mapping from the world to screen screen. Also we talked about this normalized device coordinate. So we briefly touched on some of the basic OpenGL comment structure with the frame buffer or this callback function. Then we talked about the many different types of transformations, including Euclidean transformation or affine transformations. So you probably recall that we talked about this homogeneous coordinate. So and then we actually introduced some of this basis vector to talk about these frames. Then we move on to the other this transformation within that are commonly used in the rendering pipeline: modeling transformation, viewing transformations. Also, we actually talk about this dot product, also this cross product, also this 3D rotations with this viewing transformation, also also with this projection. And then we talked about this clipping and culling. To define this culling and clipping, we talked about implicit line equation. And with the hierarchical culling, as an example of hierarchical culling, we talked about the bounding volume hierarchy. Then we move on to some other culling techniques like the Bufrosten culling, also with the backface culling. Then recently we talked about the rasterization. Also, again, to conduct this rasterization, we actually talked about the edge equations, and based on that we talked about how we can do the rasterization. Also this parameter interpolations. And then we talked about the G buffering to compute the color, also this color, also depth buffer for the visible one. Also this concept was connected with this frame buffer. And then the last time we talked about some of the simple illumination models. So we talked about ambient, term, also the ideal diffuse, ideal specular. Now we will talk about how we can do the illumination for the non-ideal specular. So last time we talked about the ideal specular reflector. At that case, we can use the Snell's law. But actually, most of objects, for example, the apples. So basically, the surface of apple is not that actually smooth, right? It actually certain the roughness. So because of due to this roughness of surface, actually the highlight actually spread out, right? So definitely we need some sort of technique to support this kind of non-ideal reflector. So there are two different approaches, right? One might be this physically based approach, but back then it's very difficult to think about it actually. What are the actually underlying the physical theory to explain this concept? Also, even though we can do that, it might require a lot of computations. So early on, we actually used this empirical model that tried to simulate the appearance of this effect without trying to capture the physics of it. Also, why we are doing that to save the computation time. So main idea is that basically this serves normal and also this light direction, and we know that we can compute the reflector direction. I mean, assuming that it's the ideal one, but since this is not ideal one, basically we can actually this surface reflecting certain amount of energy at nearby the ideal reflector direction. So basically due to this kind of the behavior, if I using the pen, so basically this indicating that once actually we have the incoming energy here, it reflect energy at an amount of direction in that direction with the amount of this energy. But other one also for other direction also that we can reflect the energy along that direction with this amount of energy. So because of this kind of property, we can actually support this kind of we can actually support this kind of spread out highlight. So along that line, basically the properties Phong illumination, this is actually one of the most commonly used, this simplistic illumination model used in computer graphics. So the setting is that this actually surface is surface normal. This is actually the incoming light direction. This is the R direction that we computed, assuming that this is actually ideal reflector. But actually this our the viewing direction. This is a the V. So basically there are certain amount of the angle difference between our viewing direction and R. So at the case of the perfect ideal specular, basically we only get the energy when the viewing direction actually align with R. For the non-ideal but for the non-ideal specular material, so we actually we wanted to give a lot of energy further when the viewing direction aligned with R. But even though there are some of the angle difference between V and R, we actually giving some of the energy for that kind of case due to this kind of roughness of the surface. So to do that, actually, we designed the reflex energy IR for that kind of the non-ideal specular term. For that non-ideal specular material, we actually this actually the Ks actually the coefficient, some sort of the material dependent the coefficient Ks, also this I is incoming energy, and then basically we if the pi is according to the pi, we actually when pi is 0, we are giving the high energy, since at that case V and R align. But as the pi actually getting a larger, we wanted to reducing down this reflected amount of energy. So along that line, actually we used this cosine term. Basically we used this cosine pi, and then also we also used this exponent term of the ns. So this cosine can be represented by the dot product between the V and R. So again, V is actually direction to the viewer, and depending on the angle of pi, the dot product between V and R can be the negative, but actually we make sure that this dot product result is clamped to in the range of 0 to 1. The specular exponent ns actually also control how quickly the highlight fall off. So for example, ns is very small. This is actually pi angle. So when n is small, it's very small, like the 0.1 energy. Actually, we are maintaining a lot of energy, but actually then it actually falls down as the pi getting very larger. In other words, actually the viewing direction is very far away from the reflection energy, the r vector. But if the ns is actually set as a very high, like the 10, basically the light actually falls quickly. So basically highlight actually quickly reducing down as the pi actually getting larger. So basically depending on these ns, we can control these highlight shapes. So this example. So this is actually this varying light direction as we change the light direction. In other words, this L, you can see the actual highlight actually the region where we have the highlight actually changing. You can see where we can actually head the incoming light direction. Also, as we changing the specular exponent, you can see that actually as we use the very low this ns value, the highlight actually spread out. But as we increase the ns, actually this spread basically this highlight actually quickly falls off, right? So by having this controlling ns term, we can actually indirectly controlling the types of the material. In other words, actually we can controlling these highlight shapes. So in summary, actually we put together all the terms together here. Then we can have this kind of shapes. So this actually the Phong illumination. So this actually in the end the reflex energy IR can be computed by the ambient term, diffuse term, or specular. This specular actually including the non-ideal specular. So basically, then you can see that this actually ambient term basically is constant, right? This actually this material dependent this the coefficient, this the light intensity for the ambient term. Also, this actually diffuse, right? Diffuse term between the normal, also the light direction. So we use the max term to actually make sure that is the dot product between two vectors will give us this positive 1, and then this actually this Phong reflection for that considering this the non-ideal considering non-ideal reflector. So basically with performing the dot product between the V and R. So basically these are the ambient diffuse specular term. And actually this also used in the OpenGL, the common OpenGL illumination model. And basically this kind of model has been used a lot, but obviously it has a lot of limitations, right? Basically this is simply the empirical models. What are the actually the then, for example, I wanted to represent this copper, this material of the copper, right? But the question is what are the actually these coefficient values? What are the Ka, Kd, Ks, right? So obviously we need to basically it's a little bit difficult to set up what are the actually this term, right? So also since these models not based on the physics, also they are not the measurable quantity. So in other words, actually basically the artist actually tried out different value and then find out some of the values to make the under the certain setting of this value, we can actually make this material looks like the copper. Also, the question is that obviously this is not a physics based one. In the end, the picture that we render is not correct, not accurate. Also, the energy also is not conserved. There are a lot of cases. So there are a lot of this the trial and error to set this one. In the end, it requires a lot of the actual very time-consuming process of the setting this coefficient. That's the main issue. So that's why recently actually a lot of the recently actually we are using the more this physically based approach. But so if you're interested, you can check it out the physics based the techniques. But here I will just introduce some of some of simplistic concepts that are based on this kind of the Phong illumination. Also, now I'd like to talk about some of the other illumination model that are using this Phong model. So as I mentioned before, basically evaluating this Phong illumination can be expensive. It requires some of the computations, also this normalization vector for especially when you have the multiple light sources. Typically, for some of this movie setting, we might need these hundreds of the light sources. So it basically it requires a lot of time. So again, also we need to evaluate this kind of illumination model for phases, vortex, or also every pixel for supporting this increasing level of this realism. Obviously, it requires more computational overhead. So that's why actually it results basically depending on this computation level, we can have the different shading models like the flat, Goro, also the Phong shading model. I will talk about each one of them. So one of simplest shading method is actually the flat shading. It actually apply only one illumination calculation for face or triangle. So in other words, let me change this pen. So given this given this triangle, we actually had this one normal, right? And then based on that, given this light vector, also given this another view vector, we can evaluate the Phong illumination. Basically, we can evaluate ambient, diffuse, specular term, right? And then we just using that based on that that term, we can compute the color, right? Then basically we use that illumination color across all pixel within the triangle. That's why across the whole triangle, it actually has the constant color. That's why it actually known as the flat. So if you actually visualize this kind of typical model, we evaluate only one Phong illumination for each this face, this quad face. So that's why you can actually have this kind of flat result. So illumination usually computed at the center of the face. For that, the central we compute the normal, right? We actually have normal. So that's why, based on that, we computed the value. So main issue is that obviously it actually has this kind of the flat result. Another one is actually this Goro shading. This is actually the researcher names. The Goro actual shading is that we can perform the illumination model on the vertices, not the center of the pixel. So it perform the Phong illumination model at the vertices. So basically, we can also compute this normal at the vertex, right? For example, if we had this kind of the triangles, suppose that I mean sometimes actually we can have we can have we can suppose that we actually had a normal for each triangle, then we can actually we can look at the given this vertex, we can look at the neighboring the triangle, we can average out these normals to compute the normal at that vertex, right? Obviously we already had this normal for each vertex, we can just use it. But if we had the only the one normal, we actually had the normal for the at the center of this triangle, we can actually we can compute it by what are the neighboring triangle for given that vertex, and then we can average them out. Then for each vertex normal, we can given this the light direction, we can evaluate the Phong illumination. We can compute the illumination. We can actually compute the color over there, right? Another color here, there, right? And then we interpolate that intensity of basically we interpolate those intensity for the remaining point on the surface. For example, for that case, if we got the illumination level of 100, and at that case we have 200 at 220, then we can interpolate across this one, right? And then also we can interpolate across this triangle. So basically this is once we computed the color intensity at each vertex, and then if we interpolate it across the triangle, that's the Goro shading. Still, if you are performing this Goro shading, we can actually still have this kind of artifact, right, across this boundary of this triangle. Since actually if we have the another triangle here, then might we have the different here actually we might the color actually basically the rate of the rate of the color changing along this triangle, that triangle actually different. So that's why we can see the kind of some of the boundary boundary shapes between across these two different triangles. So I think I already explained this concept. So if the vertex normal is not provided, for example, the normal only provided at the centroid of each triangle, they can be approximated by averaging normal of the faces which share the vertex like this, right? So given this, basically this is just equation that I just identified what are the neighboring face triangle, and then we just average out. So basically, in this case, actually, here I'm showing this wireframe of the triangle. Also, I'm showing this kind of here. This blue arrow is indicating the normal at each vertex. Now, finally, we will talk about the Phong shading. At the Goro shading, we actually interpolate the computed the illumination intensity or the color, right? But Phong shading, we can actually interpolate the surface normal. I mean, we actually interpolate the normal of the given at the vertex. So here, this one normal at this vertex, another normal here. Here actually we just interpolating the normal here. From here to there, we interpolating the normal here. And then for that part, we can also interpolate. We can actually out of these two vertex, we can also interpolate it these two vertex at the given this point, and then out of these two vertex, we can also interpolate it. Then we can compute this normal at that location or at the pixel, right? And then at that pixel, we already computed normal, and then we know we can compute it the light direction, also viewing direction, and other one, and then you can actually evaluate the Phong illumination. Main difference is that against unlike the Goro shading, here we interpolate it normal, so that's why it requires more time. We need basically we need to evaluate Phong illumination. We need to evaluate the Phong illumination at every location across this triangle. In other words, at every the pixel across this triangle. On the other hand, Goro shading, we only evaluate Phong illumination each vertex. So you can see that Phong illumination Phong shading require more computation time, since we have to interpolate normals also at each pixel of across the triangle. We also need to evaluate the Phong illumination. So then typically we can evaluate the surface. We actually performing the interpolation process based on this vertex, right? This is typically performed by the vertex shader. So before the long time ago, actually this kind of Phong illumination, also Phong shading, actually hardwired. In other words, actually GPU actually they're already actually hardwired to implement this kind of algorithm, right? But actually the GPU evolved so that actually we can even program some portion of this the rendering pipeline, and then vertex shader, basically this is the vertex shading program. So vertex shading program is that we can actually do some program. In this case, we can actually out of this given vertex, and then we can actually design this interpolating the algorithm. And then since this actually the name actually indicating that this shading program works with this vertex information. That's what we call the vertex shader. So interpolating normals from the vertex normal can be done with the vertex shader. Also, then we during this rasterizing process for it, during the suppose that we actually transform each vertex at each this we actually transform this each vertex into the sum of the pixel within the image space. Then we do the actual rasterizing, right? And then when you're rasterizing each pixel here, then we can compute the normal of there. Then we evaluate the Phong illumination, right? So that's that process conducted for each pixel, right? So also the pixel also computed as a fragment. Why do we call fragment? Basically, they could be in each pixel there could be the multiple triangle. There's one triangle, there might be another triangle, right? I mean, in the end, there could be basically we don't unless before we conducted this visibility determination, there could be basically we actually rasterize multiple triangles, and then there could be the multiple information for this pixel, right? That's we call it the fragment. And out of the basically for each pixel there could be one fragment from this triangle, another fragment from another triangle. And then by conducting this visibility determination through the depth buffering, then there could be the only one possible visible fragment that we call it final fragment that are visible at that pixel. That's why we call it actually pixel information. So typically for across this pixel, across this fragment, we can conduct this kind of Phong illumination through some of the program. So that's called fragment shader. In other words, actually we can do this fragment level the shading information. We basically you can see that we perform this fragment shader since actually this kind of shading information conducting at the pixel level, the fragment level. So basically to conduct the Phong shading, we can use the vertex shader program, also the fragment shading shader together. So let me write this one. So the Phong Phong shading usually resulted in a very smooth appearance. You can see that actually this is a result of this actually computed color when you performing the Phong shading. You can see that over the color shading we can get a much smoother result, right? But nonetheless, actually we can see that there's some sort of along the boundary shape there are some sort of the kinds of the flat shapes, right? Evidence of polygonal model can be usually seen along this kind of silhouette, right? So obviously to reduce this kind of even though this kind of the boundary shape this kind of to avoid this look of this polygonal shapes, we need to use the many triangles, or we have to use this kind of the subdivision model like this Kalman-Clark subdivision model that I talked about before. Actually, using that kind of subdivision model is very important to design the very smooth color, also even this kind of under the silhouette, also the boundary of every object, also the character. Okay, so far I talked about the Phong illumination model. Also I talked about the different types of the actual shading models. So a lot of this Phong illumination based on this local illumination. Basically, most of concept of the rasterization technique based on these local illuminations. local illumination model compute the color of the point on the surface by considering only a local property. So given this actual surface boundary, basically there's normal, and then when I rasterize this triangle, I only considering the incoming light direction of the local light, right? And then I considering what are actually the being direction, and then based on that I actually compute the sum of the light intensity, the value by evaluating the phone illumination. That's the local illumination. I only consider position of the point here. Also, I consider what are the actually surface property, the material property. Also, I look at the property of any light affected. In this case, the light direction. That's it. But when I evaluating the color here, I didn't consider other object in the scene, right? That's basically I only consider local information. I didn't consider any other information that might affect here. I mean, there could be other object here that might be blocking the light coming from that light. But I didn't consider when I talked about the phone illumination. That's why you call it local illumination. We need to consider other object, right? So basically, there might be other object that actually that may works as the light blocker or the reflector. But it's the local considering other object takes a lot of time. So actually, we only open gel or the direct X early on. This technique only consider this kind of phone illumination, which is based on the local illumination. Basically, this is the result when you consider only local illumination. But by considering the other objects, that's the actual result of the global illumination. In the real world, the light takes the indirect path. I mean, this is of normal, but there could be other object, but there are actually incoming light is actually bouncing the energy from there. Also, they bouncing the energy from there, and then we can see that, right? But actually, at the local illumination, through the phone local illumination, we cannot consider this kind of indirect direct path. Obviously global illumination we need to consider this path, so then we can actually get this actual result of by considering those indirect paths. Basically for that, considering the indirect path, we call it the global illumination. So basically at the global illumination technique, we need to consider light reflect off from the other materials. Also, the light can be blocked by the other objects. Also, light can be scattered across the band. Obviously, it is much more difficult model, a difficult model compared to local illuminations. So basically, that's why early on actually we didn't actually consider this kind of global illumination. But actually, now the GPU evolves. Also, there are more recent techniques that consider global illumination. So that's why, to considering this global illumination, the recent technique move on from the restoration technique and then move to the ray tracing. So that's why once I actually finishing on this illumination model, also the next time I talk about texture, which also very commonly used the representation across the local illumination, also the ray tracing, global illumination. Then I will talk about the ray tracing, which is actually the ray tracing actually which is very intuitive, also natural technique that consider this kind of global illumination. Also, there are many other various effects that actually by considering this there are many other effects that actually other effect that this local illumination cannot support. So, for example, this is actually this effect that are coming from the marble, also this human skin. So to consider this one, we can actually rely upon the empirical model, but it's very difficult. So in the end, we need to think about it some sort of physically based model actually. So a lot of recent technique based on this kind of physically based the model to produce this kind of the very realistic models. Also, there are still many open problems to accurately represent these kinds of represent these various natural materials. Also, there are obviously we need to actually do that in a very efficient way. So there are some of the recent techniques of paper available. So if you're interested, you can check it out, those techniques. So that's it so far. I hope that you can catch up. You can actually understand how we can consider different light during the rendering models. So we talked about the phone illumination models, including this the ambient, diffuse, also the also this phone how we can do this phone how we can consider this non-ideal reflector. That's we known as the actual phone illumination. Also, we talk about the different types of shading model, including the flat, Goro, also the even phone shading models. Actually, the phone is also one of the computer graphics researcher that developed the phone illumination model, also the phone shading. Also, I briefly touch on what are the difference between the local also global techniques. And then next time I will talk about texture mapping, which is also very commonly used further even across these local and global illuminations. Then once I'm done with this texture mapping, then I'll move on to ray tracing, which can naturally support this kind of global illumination. Okay, so these are the typical homework. Go over the next lecture slide. Submit the 2 Sigma video before the every Monday class, and then I'd like to encourage you to submit the question that naturally arise to you. You need to submit the 2 different times during the whole semester. Okay, that's it. Bye. Thank you.